All right, in this example, we're going to be using the Arrhenius equation. And the Arrhenius equation tells us how the rate constant depends on the temperature. And so we're told that for some reaction, the rate constant at 32 degrees Celsius is measured to be 0.055 inverse seconds. And we're also given the frequency factor. And we want to know what is the activation energy. So we're using the Arrhenius equation. We're solving for the activation energy. They gave us K. They gave us the frequency factor. We know R is the gas constant, and they gave us temperature. So all we have to do is work out the algebra to solve for the activation energy. The other thing we need to be careful of is they gave us the temperature in degrees Celsius. But because R is in Kelvin, I need to be sure that I convert the temperature into Kelvin. So let's do that first. So the temperature is going to be 32 degrees Celsius plus 273.15 to turn it into Kelvin. And so I get 296 Kelvin for the temperature. Now usually I like to rearrange my equation to isolate the variable that I'm solving for first and then plug in the numbers. And that's what I'm going to do here as well. So we know that K is equal to the frequency factor, E to the minus EA over RT. So the first thing I need to do to isolate the activation energy is divide both sides by A. So I'm going to write E is equal to the minus EA over RT is equal to K divided by A. The next thing I need to do to get rid of the exponent is take the natural log of both sides. So I'll do the natural log of E to the minus EA over RT is going to be equal to the natural log of K over A. And when I take the natural log of an exponential, the result is just the argument of the exponential. So that gets rid of my exponential. So then I'm left with minus EA over RT is equal to the natural log of K over A. And so now to isolate the activation energy, I'll multiply both sides by negative RT. And so the activation energy is going to be minus RT times the natural log, the rate constant, or the frequency factor. All right, and so to give myself a little more room, I'll go on to the next slide and plug in my numbers. Okay, so in red at the top, I've written what we solved for the last time, so I can just plug in my numbers now. So the activation energy is minus R, so minus 8.315, has units of joules per mole times Kelvin. Multiply that by the temperature, which we said was 296 Kelvin. And then that's times the natural log of the rate constant, 0.055 seconds to the minus 1, over the frequency factor, which they gave us to be 1.2 times 10 to the 11 seconds to the minus 1. And when I check my units here, right, so seconds to the minus 1s cancel, so there's no units inside the natural logarithm. And then I have joules per mole dot Kelvin times Kelvin, so the Kelvins will cancel. So I know my units will come out to be joules per mole. And so my activation energy to three significant figures comes out to be 69,900 joules per mole. And the problem didn't ask us to do this, but very often we report activation energies in kilojoules per mole. So to convert that to kilojoules per mole, the activation energy is 69.9 kilojoules per mole.